Dear students, in this class, we'll discuss about Joule-Thomson effect. So, this is related to liquefaction of gases. So, what is the Joule-Thomson effect? When a compressed gas is allowed to expand through a small hole, the cooling effect takes place. That cooling effect caused, and when the cooling effect takes place, the temperature falls down. So that effect is known as the Joule-Thomson effect. So it was observed below a certain temperature. So that temperature will be different for different gases. So it is related to Van der Waals equation. So that is Ti is equal to inversion temperature, that is equal to 2A by RB. So that cooling effect is caused only during expansion if the temperature of the gas is less than that particular Ti. So if the temperature is greater than Ti, heating effect, that is a negative Joule-Thomson effect is observed. So the expansion of gas as the Ti does not show cooling or heating effect. So that means if it is not showing any cooling effect or heating effect at Ti, so the Joule-Thomson effect is said to be zero. It is said to be zero. So inversion temperature. So the inversion temperature of a gas can be defined as above the temperature at which the Joule-Thomson effect becomes zero. So that is a Ti. That is I told before itself. So that is Ti is nothing but inversion temperature. So inversion temperature is the temperature at which the Joule-Thomson effect becomes zero. So Ti is equal to 2A by RT. So what is a critical phenomenon? So from this critical phenomenon only critical constants will be produced. So by applying at low temperature and high pressure, the gas will be liquefied. So when a gas will be liquefied, that means the gas can be converted into liquid state by applying low temperature and high pressure. So by cooling, when we are decreasing the temperature, that is nothing but cooling, what happens? The kinetic energy of the gas molecules decreases. So then the molecules come closer to each other, so that the attractive forces that are between the molecules increases. So due to interactions in the gas molecules, the gas converts into liquid state. And so essential condition is given by Andrews by the result of PVT, so pressure volume temperature relationship of carbon dioxide. So it was the temperature above which the gas cannot be liquefied. So however, the pressure is applied. So that temperature is known as critical temperature. So critical temperature, the temperature below which the gas can be liquefied by the application of pressure. The gas cannot be liquefied by the application of pressure. So what is critical pressure? So critical temperature is denoted by Tc, whereas critical pressure is denoted by Pc. So what is critical pressure? The pressure required to liquefy a particular gas at critical temperature. And critical volume, so the volume occupied by 1 mole of substance at both the conditions. That means at critical temperature as well as critical pressure. So that volume is known as critical volume. So Joule-Thomson effect illustration. So if you see, if you are considering the example, so the graph plotted between the pressure and volume at different temperatures. So we can observe the graphs between pressure and volume at different temperatures, but at CO2. So that means these are the isotherms. This graph is called isotherms. So we are plotting the graph between pressure and volume at a different temperatures. So this is the isotherm for carbon dioxide. So if you are considering an isotherm at 13.1 degrees centigrade, at low pressure, what is happening? At low pressure, the carbon dioxide is completely in gaseous state and is represented at point A in that particular isotherm. When we are increasing the pressure, the what happens? So since pressure and volume are inversely proportional to each other, on increasing the pressure, the volume decreases as shown by the portion AX of the isotherm. At X, what is happening? The deviation is being observed from the Boyle's law begins to appear and the volume decreases rapidly and the gas will be converted into liquid state. So at a point Y, the carbon dioxide is completely converted into liquid state. That means it is completely liquefied. So between X and Y, the pressure remains constant and both the gas as well as the liquid phases are in equilibrium. So the pressure corresponding to the horizontal position XY of the isotherm is the vapor pressure of the liquid at the temperature of isotherm. So the isotherm, which is at 21.5 degrees, also shows the similar behavior. When we are increasing the temperature, the horizontal portion of the particular isotherm becomes smaller and smaller until 31.1 degrees centigrade, which it is reduced to point P. So that point P is called critical point. So at this critical point, the boundary between the liquid and gaseous phase disappears. So meniscus, upper meniscus as well as lower meniscus, the meniscus disappears, indicating that both the phases are having same characteristics. So above 31.1 degrees centigrade, so there is no indication of liquefaction. The isotherm at critical temperature, that is 31.1 degrees centigrade, is called critical isotherm. Critical isotherm. The tangent at critical point P is horizontal such that dP by dV at critical point will be 0. So that point P at which the critical point will be 0, that is known as the point of inflection. The point of inflection. So in the area that is being to the left of the dotted line, below the critical isotherm, only a liquid carbon dioxide exists. So the horizontal portion within the dotted line shows that equilibrium exists between the gas phase as well as liquid phase. So Vc, that is critical point, critical volume. So Vc is equal to 3B. Pc, that is critical pressure, is equal to A by 27B square. Tc is a critical temperature, which is indicated by 8A by 27 RB. So we can express the constants A, B and R in the form of critical constants as B is equal to Vc by 3, A is equal to 3Pc Vc square, R is equal to 8Pc Vc square by 3Tc. So these are the different critical constants of different gases. So next, the order of liquefaction or the order of liquefaction, if you see, SO2 is quickly converted into liquid state, then water, then ammonia, carbon dioxide and water. So incompressibility of a gas. So Van der Waals constant, I told there are two different constants, A and B. So the B represents the excluded volume, which is 4 times the volume occupied by the gas per molecule, and the value of B remains constant over a wide range of temperature and pressure, which indicates that the gas molecules are incompressible. With that, I will conclude the session. In the next class, we will discuss about the remaining topics.